So let's see fourth experiment 4.2 with respect to mesh current analysis with respect to nonlinear circuits. That is when we have the passive elements L and C, AC circuits. So aim and application. So we are seeing the application of mesh current analysis for the given circuit to determine the values of Ix, Iy and Iz and verify the same using PSpice. Now let's do the theoretical calculations and then verify in simulation. Now for calculations one has to verify that all your passive elements are in ohms here, that is in your phase domain. So we have R in ohms, but we have C in farads and L in Henry. So how does one convert to XL and to XC? What are these formulas? The formula for XL is omega into L. The formula for XC is 1 by omega C. Now to find XL and XC we need omega. So what is omega? Should we assume or is it given in the question? In the circuit diagram you can see this 2. So this is as same as 10 cos omega t or 6 sin omega t. So this omega should be constant in your circuit, else you cannot solve by directly applying mesh or nodal. You have to use the method of superposition theorem to solve. So we'll see that later. So omega in this case is 2 radians per second. So when you substitute it, you get the value of XL as 4I ohms. We have to suffix I. I hope that I hope that is known to you. That's been taught in your first year basic electrical engineering. Similarly, XC would be 1 by 2 into 0.25. I get the value of XC as minus 2I ohms. I hope you are aware that why are we substituting the value plus I and minus I. Now by these values let us rewrite the circuit as shown here. Right, now we have solved, we have all the values, all the passive elements in ohms. However, we have two trigonometric functions. So let us replace this 10 cos 2t in terms of sine, and then your answer would be 10 sine 2t plus 90 degree. Right? Now this can be written in polar form as 10 at an angle of 90 volt, and similarly 6 sine 2t. What is the angle? The angle is 0, so I can rewrite this in polar form as 6 at an angle 0 volt. Right. So now the reduced circuit, you have the circuit reduced in this way. So instead of 10 cos 2t, we'll take that as 10 at an angle of 90. And instead of 6 sine 2t, we'll take that as 6 at an angle of 0 to solve. So let's see how do we solve by applying mesh current analysis. So mesh 1, we'll assume the current in clockwise, that is the same orientation of Ix, and mesh 2, we'll assume the same orientation of Iy, that is in anti-clockwise direction. And one can see the polarity across capacitance as plus minus with respect to Ix and plus minus again with respect to Iy. So let's apply mesh current analysis here. Mesh 1, it is 4 Ix minus 2I Ix minus 2I Iy, I'll say equal to 10 at an angle of 90. So we rewrite this as 4 minus 2I Ix minus 2I Iy is equal to 10 at an angle of 90. So this is my first equation. Let's apply for mesh 2. We get in anti-clockwise the equation is 4I Iy minus 2I Iy minus 2I Ix, and then equal to, we get minus 6 at an angle 0 equal to 0, or shifting the constant on the right LHS, we get this as 6 at an angle of 0. Right? So when we rewrite this, we get this as minus 2I Ix plus, so you can see we have 4I and 2I, they cancel each other, and the final result is plus 2I Iy is equal to 6 at an angle of 0. This is my second equation. Let's rewrite this in matrix form. 4 minus 2y, we have minus 2y, and then minus 2i and then 2i. Column matrix for current is ix, iy, and then the voltage 10 at an angle 90, 6 at an angle 0. Now, how do we find the value of ix and the value of iy? The value of ix is given by Kramer rule as delta ix by delta and iy as delta iy by delta. So let's move on forward to find delta. This is the values of delta. So let's find what is your delta. So delta is nothing but determinant of this matrix. So delta is given as 4 minus 2i into minus I, negative of minus 2i and minus 2i. And the answer you should get that as 8 plus 8i. Oh, I'm sorry, there's a small mistake here. So this should be positive here. Now it's correct. So 4 minus 2i into 2i, and the negative of minus 2i into minus 2i, you should get 8 plus 8i. So let's find out what is delta ix. So how do we find delta ix? You replace the column of ix with respect to iy. So here we have two columns, out of which this belongs to ix, this column belongs to iy as you multiply them. So replace your ix column with constant. That's 90, 10 at an angle 0, 10 at an angle 90, and 6 at an angle 0, and then your iy as it is. Now, determinant of this is your delta ix. Right, 10 at an angle 90 into 2i minus of 6 at an angle 0 into minus 2i. And when you solve, you will get the answer as minus 20 plus 12i. And now your ix is given by Kramer rule delta ix by ix, which is nothing but, I'm sorry, it's not delta ix by ix, it is delta ix by delta. Minus 20 plus 12i in parenthesis whole divided by 8 plus 8i. The answer in polar form is 2.062 at an angle 104.036 ampere. So this is your answer for ix. Let's move on now and solve for iy. Same matrix, one is to solve for iy. So iy is given as delta iy by delta. We've already solved for delta is 8 plus 8i. The only one thing that we have to find is delta iy. So how do we solve for delta iy? So replace your second column, which is associated with the delta iy, with constant. That is 10 at an angle of 90 and 6 at an angle of 0. So when you find out the determinant of this, you should get your answer for delta iy. When you solve, you will get the answer as 4 minus 12i. So substitute that here, 4 minus 12i, the whole divided by 8 plus 8i, you get the answer as, answer in polar form, 1.118 at an angle minus 116.56 ampere. Now, what is the answer for iz? So what is the answer for iz with respect to ix and iy? It is simply ix plus iy. So when we add, we get the answer in polar form as 1415 at an angle 134.99. Right. So let's write down all the answers together. This is 2.062 the angle, similarly iy and iz. So now the aim of the experiment is application of mesh current analysis to an AC circuit to find out ix, iy and iz. Now let us simulate and find out or verify our results. Click on schematics. Now what are the part names that are required? The circuit connection in PSpice. So what all are the part names that are required? The components required are one resistance, one inductance, one capacitance, and two sinusoidal voltage and one analog ground. So as you can see, when we had solved, I'm sorry, there's a small mistake here. This is 2 Henry. So when we had solved, we had taken all the passive elements in ohms, but in simulation, we'll take the values as the values in resistance, inductance, and capacitance. So let's go to PSpice and try to build the circuit. Let's take the parts. That is resistance. Part name is inductance L. The part name for capacitance is C. Control R to rotate, place it vertically. And as told, it is VSIN, V sign. We need 2 voltage sources, analog voltage source, and 1 analog ground, A, G, and D. Now we've got all the parts zoomed to fit. Now let us connect, and then you can revalue the active and passive components. Now we have connected. So the resistance is 4 ohm and the capacitance is 0.25. Do not give farad because F stands for 10 power minus 1.5 in PSpice, and inductance is 2 Henry. You can give 2H here. Now V1. What is the data for V1? DC is 0, AC is 1 as it's an AC source, which will enable that. V off is 0, that's voltage offset. Now V amplitude. The amplitude is 10, as we have seen. Frequency. What is our frequency? So did we calculate frequency? Now we know the value of omega as 2, and the value of F. The value of F is nothing but omega by 2 pi. That is nothing but 2 by 2 pi. That is 1 by pi. And the value of inverse of pi is, we'll take up to 4 decimal points. That is 0.3183 hertz. Right? So this is your frequency. So let's enter the value of frequency. How much? That is 0.3183. I'll copy this because we need this for another voltage source which is having same angular velocity. Save attribute. Then, if you can remember, we had taken our input as, we have converted the cos to sine, and the value of theta was 90. Right? So when simulation, in calculation, what we did, we have taken this as 10 at an angle of 90, converted cos to sine. Right? Same thing has to be incorporated here because we have sine wave. We do not have cos wave here. Right? So I'm converting this cos to sine by replacing phase angle as 90, save attribute. Click on V2, the same parameter, DC is 0, AC is 1, V off is 0 as discussed in the second experiment, and V amplitude is 6. Frequency, I've just copied, so 0.3183 hertz, and then angle should be 0 as by default it is sine wave. Save attributes, click on OK. Alright, let's save the file as experiment 402. Now, as we build the circuit, we have labeled it. All we must do is simulate. Now, where should I keep the current marker to find Ix? So, which branch current will give me mesh current? So, current through 4 ohms will give me the mesh current and the branch current Ix. And the current through L1 will give me Iy. But where should I place? To the right or to the left? Since I want the current going left in anti-clockwise, I must place at here. Right? And Iz I want it down, so I will be placing the current marker upwards. Once we have done that, let us rename the values R1, L1 and C1 to Ix, Iy and Iz, so that it will be very easy that you have observed in your second experiment. So we'll rename the values so that we can directly see and compare our results with Ix, Iy and Iz. Now save your file. Now before going to simulation, we have to enable transients and let me discuss. Should I change the values of print time and final time here? If yes, then what should the values be? Let's discuss on these points now. Now what's our frequency? Our frequency is 0.3183 Hertz. And what is the time period? Time period is 1 by f, which is nothing but pi. That is 3.14 seconds. What do you understand by this time period t? So time period t is it says that one cycle takes around 3.14 or pi seconds. So what should my final time be in PSpice? So if you remember in the second experiment we had given 1 seconds. So can I set as 1 seconds is my question. If I set as 1 second, I'll get less than half a cycle to view. If I give as 3.14, I can see one complete cycle. So let's see that I want to see 15 cycle. Why do I need more cycles to observe? Why can't I just give 1 cycle or 2 cycle and find the peak value? I hope you know the answer. So let me discuss. We are giving more number of cycles because we know initially there will be some disturbances in the circuit because of, can I think of the answer? It's because of charging and discharging of voltage across capacitance and current through inductance. That's the only reason why we have to give as much as time possible. So now let us say we give some time and we have still disturbance. What you can do, you can go back to your circuit, go to setup analysis, go to transients, and then enable transient and click on transient and change your time, increase your time until unless you get steady state. So what I'll do here is I just want to see 15 cycles. So what I'll do, 1 cycle is pi into 15 cycle. So what is pi into 15? It's approximately, not approximately, it is 47.12. So I'll be giving as 50 cycles, 50 seconds. So that I can see around 15 to 16 cycles. So I'll go back here, I'll change into 1 second, I'll give 50s. So in your exam, as the omega changes, the value of frequency changes and your time period changes, right? So this is what you must take care in your CIE, right? So this is your this is how we test your understanding of your concepts. Now we have entered the value, we have entered the V1, the V1, V2, we want to set up analysis, given the time period that how much waveform we can see, save your file and then click on simulate. What we'll be doing? We'll be simulating our circuit connection in PSpice to check your outputs. So we have got our output. So let us compare this with our theoretical calculations. So Ix we have got 2.062. Let us start with that. So once you have got your output, click on toggle cursor. You can see here we have Ix, Iy and Iz. It's very easy to now analyze. However, you have kept the Ix correctly and similarly Iy and Iz. You have placed your current markers correctly so that you can see your accurate answers. So click on cursor peak and let us see what is the constant value that we see. 2.0639, 640, 640, 641, 2, 3, 4. Right? So I think 0.0643 is constant, but you can see I got only for 2 cycles constant. Now what I'll do is I'll go back to simulation. I'll change my time. Instead of 50, I'll give 100. Okay, instead of 50, I'm giving 100 seconds. And I'll re-simulate just to make sure I have steady state. So now let me check. You can see here it's changed to 100. So let me find the toggle cursor. Yes, cursor peak. Let's see the constant value. You can see it is still changing. As it is still changing, what I'll do is I'll go to setup analysis and I'll change the transient time to 1000. Right? And when we simulate, you can see I have 1 kilohertz, and let's see now do we get our peak value constant. So I'm checking for Ix. So let me randomly push here and check the peak value. I'm getting 2.07. You can see it's still changing. 2.0733 became 7.4, 7.5. It's changing slowly. right? So still there is disturbances. So what we can do is we can just fix the value as 2.062. Where do we find 2.062? So let's somewhere see here. Yes. So 2.062, we'll try to search the value. Now the easy way to search this value is click on cursor search and you are searching the value. So SFLE 2.062. Okay, let's move the cursor forward. Use the same code and then click on OK. Oh, I have typed it as 20. You have to type 2.02. Okay, so this is where we have got. Right? So approximately the values are matching in your PSpice. So still the circuit is not settled, right? So then afterwards, let's find for IY. So click on IY. So click on cursor peak. So 9, approximately 1 milli. Right? You can see approximately we have 973.974 and then 978. It's slowly increasing. So still we have disturbances. So you can pick any value here as your reference value of your magnitude, as we have still disturbances, right? So I'll pick the value as approximately 983 milliamperes. So I'll write down here the value of current. So IY in simulation we have got 983 milliampere and this as 2.062 ampere. So we are searching only for the magnitude. Now similarly, let's do for IZ. So click on this blue color icon, bring your cursor backwards, slightly move it forward and then search for cursor peak. 1.47 is the answer, but we have got 1.14, right? So let's see initially what is the disturbance. So let's try to zoom in. Yes, let's try to see it here. 1.47, 472, right? So we'll take the answer as 1.472 amperes. These are your magnitudes. Why is it not same? Because we can see we have still disturbances. It might take more time to settle, right? So we'll fix these as our answers, and these are your answers for magnitude of your current IX, IY and IZ. Now let's try to find out the angles. Let's start with IX. The angle is 104.036. Now how do you find? So where you should keep your reference? You should keep your reference after disturbance. So let's keep somewhere after 2.62 amperes. So let's go back to simulation and let's delete IY and IZ so that it will be easy. What you can do is you can select here and just press delete button in your keypad. Let's zoom to fit and let us click on toggle cursor. Search when did you get the value 2.062. So search for the value along y-axis and the value is 2.062, right? So what is the time? At 300 approximately, let us take 300.35 milli. So IX, the peak value is 2.062 amperes. At what time? At your time 300.535 milliseconds, correct? Yes, we have here milli. You can observe here we have at milli. Let me zoom in to show you that. You can see at here we have got that peak value. Right? No, we can't consider that. Right? So let me show you. We cannot consider that value. So you can observe here. So that value is here, but still we have disturbances. Right? So let's see where you do not have least disturbances. So let's go back here. Let me zoom in less area. Okay. Now let us try to check within 50 cycles. So we'll try to find out the value somewhere between 20 to 30 seconds. Okay. So we'll say let us say that after 20 seconds is somewhat stable, right? So we'll say we have disturbance till 20 seconds. So we'll see our reference point after 20 seconds. Now how do we do that? So we know the time period is pi. Pi into something should be greater than 20 seconds. So how do we do that? Simply multiply pi into 10 cycles and I'll simply get 1.415 seconds. So I'll consider this as my reference for all your currents for Ix, Iy and Iz. Because we have still disturbances, so I'm considering this, assuming that there are less disturbances or there are disturbances until 20 seconds, and after that it is slightly better. So my reference point would be 31.45 seconds. Now let us see how do we find this. Then we'll go on to PSpice and solve. Now that I've taken that origin of disturbances, so I'll be placing my cursor, A1 cursor, at the time 31.415. Let's do that first. What is the code? And what is this? Is this x-axis or is this y-axis? This is x. As you can see, it is in seconds. And the code for this is search for x value 31.415. Let's do this first and come back. So click on toggle cursor again. Go to cursor search. Type the code SFXV 31.415. Yes, now we can see this is our new reference. So I'll try to zoom in and see how do we find our angle. Now we found this. Now Ix, what is the angle? Our angle is positive. So should I see to the left of the region or to the right of the reference point? Now to find positive theta, one has to see towards the left, and to find negative theta, one has to see towards right. Because voltage is what we have given input, current is actually leading. Right? So that means my waveform is somewhere like this, and I have to see this zero crossing, and to find this delta t. Right? So what do? I should place my A2 cursor. Let me take a different color here. So I have to place my A2 cursor before the reference and I have to move backwards. And the code for that is SBLE0. That is search backwards. That is search towards the origin. And what value should I search? I should search the value 0 along y axis. So let me do that here. Cursor search. Now before that you have to select your, you have to right click. So right click where? You have to right click before your reference here. Right. So what you can do is you can slightly come back and then move backwards. Then I'll show you what happens. So let us say you right click here and you type the code, and you can see I think we have left clicked. Yes, you can see the cursor for A1 is shifted. The cursor was 31.41. So again you click on cursor search. Just the code is already there. Just type. Yes, now it is there. You have the reference point. Now you can right click. Let us say you right click and stop here, and you type the code. So you can see as you right click, cursor 2 is selected. SPLE, search backwards, the value 0, and then click on OK. It went backwards. If it's not going backwards, you can drag slightly backward and then type the code. Now what is your delta t? Your delta t is 915.011 m. Right? So let me write that here. So the value of delta t is 915.011 m. 011 m. So this is your delta t. Now How do you convert delta t to theta? Let's see that in the next slide. Now 915.11m. In the formula, this is your delta t. To find theta, formula is delta t into 360 into f. And what do we get? Delta t into 360. And what is your frequency? Frequency is, we have taken that as 0.31. We have taken up to 4 decimal points. So when you multiply, you will get the answer as this is the answer for Ix. So when we have solved, theoretically we have got 104.036 and now we are getting 104.849. Why is this deviation of answer? Because still we have some disturbances. Now let us try to find the angle for Iy. What is the answer here? Minus 116.576. So where should we find the angle? So negative region, as you can see, first we have to select your Iy current and then we have to simulate. So let's do that. Let's write down the value for the theta for, what is the theta for Iy? The theta for Iy is minus 116.565 degree. Let's see how do we do this in PSpice. So Iy minus 116.565. Let's go to simulation. Let's delete. Instead of doing this, I'll tell you. You can click on here and click on this play button. You can see you get again Ix, Iy and Iz. So let's delete Iz and Iy, and as told, we have to select our reference as, what is our reference that we must select? 31 point. We'll just go back to the next slide, the previous slide, and see. The reference is 31.415. 31.415 is our reference. Process search the value, search the x value, SFXV 31.415, click on OK. Now let us zoom in here to find the answer of theta. Okay. Now where exactly should we, or how do we find the answer? Now this is our A1 cursor, which is our reference, and what you have taken this as 31.415. Now for minus theta, we have to see at this region. That means we'll have a waveform at somewhere here, it will be crossing 0, right? And we have to find this delta t, this time difference, right, from the reference to the 0 crossing of your waveform. Now right click, and where you have to right click? After your reference. So right click after your reference, and you can see as I right click, cursor 2 is selected. Now how should we move? As you can see, 0 is somewhere, it is crossing here. You can see if I draw a line, if I draw the line here, the 0, right, it is somewhere hitting the line here, curve here. So I should move forward, and the code for that is SFLE. Search along your y-axis for the value 0. Yes. And now the difference between these two, is your delta, right? And you can see I've got the answer as minus 1.0065. We've got now delta t as minus 1.0065. So the value of theta for Iy is delta t into 360 into frequency, and when I substitute that, we'll get the answer as minus 115.33 degree. Sorry. Now let's find for Iz. Z is 1.14 that we have seen, we found out in PSpice magnitude. Now let's find the theta for Iz. So we have got positive 134.8 989 degree. Now, so where do we see? If this is my A1 cursor and we know the time is 31.415, and to find plus theta, you have to see towards the left of your origin. So I'll be having a zero crossing somewhere here. So you have to find out this delta t and then find out the theta as delta t into 360 into frequency. So let's take IZ. So click on the play button. You'll have all the three. Delete by selecting IX and then using delete button. Now the time period that you've taken is selected as SFXV 31.4. I think it's 415. Let us check in our previous steps what we have done. Is 31.415. Now this is my reference, so I'll just zoom. So what you can do, again click on cursor sets, the code will be present. Just click on OK, it will go back. So I'm zooming in to show you. So here is our reference. This is my reference to find plus theta. So this is your zero crossing. I have to place I should right click and place my cursor somewhere here. Doing it manually is difficult. So what you can do is right click, right, and move along the backward direction. Click on cursor search. You can see as I right click, the cursor 2 is already selected. As I must move backward, the code is SBLE 0 and then enter. So you can see it moved backward, it is towards origin and it has placed. And the value is 1.1352. 1.1352. So delta t is 1.1352. And then when you substitute that, you get the value of theta as right. So we're getting the deviations in answer for Ix, Iy, Iz for both magnitude and angle, because still we have some disturbances. The circuit is taking more time for steady state, right? So this is how we have to simulate, and first you have to calculate, then you'll be allowed for simulation, and then you have to compare your answers with the theoretical calculation and simulation, and then write your comments. So the comment would be why the answers are slightly deviating, because the system is taking more time for settling. You can see we've given 1000 seconds. As you give much more, probably it will take even more time for it to settle. Next. And the input waveform is cos. Remember that we have converted that into sine. That should not be a trouble. And the frequency, we have taken omega. Omega is exactly 2. It's a whole number. But when you have given the input in simulation for frequency, the answer is taken in few decimal points. And that is also one of the reasons why the system is taking more time for settling. Now you could ask, why can't we give omega itself? It's not designed here currently in PSpice. So this is your result by comparing the theoretical and simulation calculations.